Okay, hopefully you can see this okay. So I have, for the first potential, I have it broken up into 4 different regions. Region 1, Region 2, Region 3, and Region 4. We have an infinite wall here at negative A, and then a finite barrier from 0 to B. So we define the potential as a piecewise function, which is 0 for our x greater than or equal to b, v naught from 0 to b, 0 from negative a to 0, and then infinity for x less than a. So if we set up our Schrodinger equation, we do it for each boundary, each region. There's 2 cases, E greater than V naught or E less than V naught. And we imagine shooting particles in from the right. So they're going to come in and they're going to hit, for E less than V naught, they're going to hit this potential barrier, and due to quantum mechanical effects, we'll have some tunneling. So we'll have a decaying exponential in here. Then we will also get transmission through that, and then once it hits this potential barrier, we'll have full reflection. So we decided there will be no bound states for this, and we'll have all scattering states for this setup. So once we set up our Schrodinger equation, we find the energy eigenvalues of the wave function. And this will be, for the sake of time, I'm just going to set up the equation. V is 0 here, so we'll end up with something looking like this. And if we define a constant K1 equals square root of 2me over h bar, we will get a solution that looks like this for a wave function in region 1. Okay, that's region 1. Now for region 2, we have V naught now, so we can't set it up the same way here. We're going to get a little bit different. We set up our time-independent Schrodinger equation. Now we have V naught for our Hamiltonian. And I can combine like terms to get this equation. And then carry through again, and we'll get second partial derivative of the wave function equals negative 2m times E minus V naught over h bar squared psi. Okay, hopefully you can see that. And if we carry through this negative sign, so I'll get 2m V naught minus E psi over h bar squared. Define K2 to equal square root of 2m V naught minus E over h bar. So that is if E is less than V naught. If E is greater than V naught, we define K2 as square root of 2m E minus V naught over h bar. The first case, hold on, I'm filming this in a very awkward position because I have no camera or way to hold the phone. So in the first case, the solution will be CE to the K2x plus DE to the negative K2x equals psi 2 of x for E less than V naught, so decaying exponentials, or it will be CE to the I K2x plus DE to the negative I K2x equals psi 2 of x for E greater than V naught. For region 3, I'm not going to go over the derivation again. It's going to be identical to region 1 with the same k value. So we'll get e to the I k1x plus fe to the negative I k1x. And to tell you the truth, I'm going to use F and G, so I don't want to confuse it with the energy. So F and G equals psi 3 of x. Region 4, no particles are going to penetrate through this barrier, so therefore a wave function in region 4 has to equal 0. So now it's time to define the boundary conditions. So we know the wave function has to be continuous at the boundary, so wave function in 4 has to equal wave function 3 at x equals a. Wave function 3 has to equal wave function 2 at x equals 0. And wave function 2 has to equal wave function 1 at x equals b. Also, their derivatives have to equal each other, except for, I believe, at a, because we have infinite potential here. So let me write those down. Wave function 4 at negative a has to equal wave function 3 at negative a. Wave function 3 at 0 has to equal wave function 2 at 0, and wave function 2 at b has to equal wave function 1 at b. Then the derivatives, wave function 2 or 3 prime at 0 is equal wave function 2 prime at 0, and wave function 2 prime at b has to equal wave function 1 prime at b. Okay, so let me carry out those boundary conditions for you. Okay. So we're going to get, for the fourth equation, for the fourth region and third region, we'll get e to the I k1a, plugging in negative a, plus I k1a equals 0 because the wave function 4 is 0. Then for 3 and 2, we'll get, plugging in 0, c plus d equals e plus f, and also hold on, k2 c minus d equals I k1. Hold on, I'm getting confused. I k1 e minus f. Yeah. Yeah, so that's 2 and 3. And then 2 and 1, we'll get a e to the I k1b plus b e to the negative I k1b equals c e k2b plus d e to the negative k2b. And then the derivative I k1a e to the I k1b equals, minus I k1 b e to the I k1 b equals k2 c e to the k2 b minus k2 d e to the negative k2 b. So the only thing that's going to change, and for the sake of time, if E was greater than V naught, is that these will be complex exponentials and there will be an I here. So my approach was to solve for the reflection coefficient should be the total reflected probability, which is B, over the total incoming probability, B squared over A squared. So we need to get everything in terms of, my approach was to solve for F here and get everything in terms of F. And that derivation will be on the paper that I submit. And I also tried to put it in Python to get the actual values, but I attempted it on paper as well.